Okay, today we're going to get started on statistical tests for means. We're going to start with a one sample test for means. So let's go ahead and take a look at the example problem. Let's get it all centered. The EPA has determined that safe drinking water should have an average pH of 7. Water is unsafe if it deviates too far from 7 in either direction. You are testing water from a new source and randomly select 30 vials of water. The mean pH level is 6.4, which is slightly acidic. The standard deviation is 0.5. Do the data provide convincing evidence that the alpha equal 0.05 significance level that the true mean pH of water from this source differs from 7? So again, we're going to do phantoms. P, we state our parameter in this case. Mu is the true mean pH of all water from this new source. Okay, so we always kind of want to start off mu. There's going to be no numbers here. It's only going to be our notations. H is our hypotheses. Much like with proportions, we have a null, we have an alternative. And in this case, the null is the claim. We're going to say that it's safe. The alternative in this case is going to be that it's not 7 because it says either direction and it also says differs. Both of those mean, and that's called a two-sided test. So in actuality, what this is going to be doing is it's going to be looking to see if it is on either side of 7. So basically it's going to look and see if it's 7, it wants to know if it's either this way or this way, because if it goes either direction, it's not safe. A, we're going to validate our assumptions. We start off with random. And in this case, we're going to go ahead and say it states random in the problem, states randomly select. So this tells us we're dealing with an observational study. So that helps us with independent. Independent is our next check, and our independent is our 10n check. So we're going to do 10 times our sample size. In this case, we're going to do 10 times 30. And that's 300. We're going to compare that to n. Do you think it's safe to assume there are more than 300 vials of water from this new water source? I'm going to say yes, safe to assume more than 300 vials of water from this new source. Okay. Next one is going to be my large enough check. And my large enough check, there's the 3 things you go through in order. First thing we look and see, does it say the population is normal? Nowhere in there does it say the population is normal. So we move to the next stage, which is our sample size. Our sample size is 30. That's greater than or equal to 30. So by the central limit theorem, we can describe this distribution as approximately normal. So we validated all of our conditions. And now what we want to do is we move to our next step, our n. We're going to name what we're going to do. We're going to conduct a one sample T-test for true mean at alpha equals 0.05. Let's go ahead and just put the degrees of freedom down here just so we have them. So we know that our degrees of freedom are n minus 1. So 30 minus 1, our degrees of freedom here are 29. Now T. The way this is going to work, our T formula is as follows. T equals x bar minus mu over Sx squared of n. Let me just kind of give again a general area of where you can look for this on your formula sheet. When we look down here and we see the standardized test statistic, it's statistic minus parameter over standard error. So that's the general form that gives me that. Flip over to the back of that page. We're talking x bar as a statistic. There's our standard error, that's our denominator. And we're going to use the mu as our mean. So now what's going to happen is I'm going to go to my calculator. My calculator is going to do most of the heavy lifting. So again, what I'm going to do is I'm going to go to stat. I'm going to go to tests. I'm going to do number 2 as a t-test. We can either do data or we can do stats. In this case, we're going to go with stats because they gave us stats in the problem. The stats they gave us in the problem were as follows. They told us that the X bar was 6.4. We know that the mean, that's our 7, that's what we say is the claim, divided by our standard deviation, which is 0.5, divided by the square root of n, 30. This is going to give us like a standardized score, like what we had that z-score before. It's just a t-score. So we're going to use stats. Our claim is 7. Our mean is 6.4. Our standard deviation is 0.5. Our sample size is 30. And in this case, we want to do the not equal to, the two-sided test. We're going to go ahead and we're going to calculate. And what that is going to tell us is we got a really, really, really tiny t statistic, negative 6.57. This is negative 6.57. So what it's saying is this sample that we pulled was almost more than 6.5 standard deviations below average. So in other words, if I kind of looked at this visually, and I drew myself the curve, this would be where 7 would fall. So this is saying if we had truly had a pH level of 7, this is what the sampling distribution would be. We were like way over here. So this is really, really a significant result. And in this case, we got a p-value. It says 3.3. That's our O to get the p-value. Now remember, when you see that E, it means moving the decimal point to the left. So in this case, we are moving the decimal point way, way, way to the left on this one. So what we end up having here is we have a p-value that is equal to essentially 0. I mean, because when you are talking about 3 to the times 10 to the negative 7, this is what we're talking about. 1, 2, 3, 4, 5, 6, 3. It's an incredibly small number. So now we have our p-value. We make our decision. Our p-value is less than our alpha because basically 0 is less than 0.05. So in this case, we would reject the null hypothesis. And then our final step is that sentence. Since the p-value of essentially 0 is less than our significance level alpha of 0.05, we reject the null. There is evidence to conclude the pH level of this new water source differs from 7. And in this case, it said it was slightly acidic. So basically, we're going to find out that this water is probably too acidic. So that is how we run a significance test. We kind of go through this whole phantoms process. So let me kind of zoom out so you can see the whole thing at once. So the way we run through that test again is we do stating our parameter, our hypotheses, validate our assumptions, say what we're going to do it. And really honestly, what we're going to do is we're going to do that part right there. Figure out our p-value from the calculator, make our decision, then state our statement. And that's kind of how we run a significance test. So now what I want to do is I want to show you the kind of follow-up questions that come from this. So here we go. Here's our first follow-up question. Our first follow-up question says, a 95% confidence interval for the true mean pH water level is 6.21 to 6.59. This is a thing we are 95% confident. The interval from pH 6.21 to pH 6.59 captures the true mean pH level of water from this new source. Okay, so there's our first kind of question is, again, that's going back to our intervals. Part C, explain why the interval in part B is consistent with the result in part A. Well, here's the thing. We did a two-sided test. Our test was a not equal to situation. A two-sided test is consistent with a confidence interval. What it means is, if you think about when you work with a confidence interval, we do our point estimate plus or minus our margin of error. So what we actually do is we actually look in both directions. We go up, we go down. When we do a two-sided test, we're kind of looking at that sampling distribution. We're looking down, we're looking up. What it doesn't coincide with, or what it doesn't is not consistent with, is if I had done a one-sided test. So what I mean is this. If I had done a one-sided test, and what a one-sided test is, let's just say I was doing a one-sided test to greater than. Again, we have that sampling distribution. I'm only caring about this. My alpha is all going to be over here, so I'm only looking at this side. If I tried to compare that to a confidence interval, a point estimate, plus or minus a margin of error, like I said, this looks in both directions. So it's not apples to apples. This one, I put all of the outside stuff on one. This one, I have ranges of values in either direction. So in this case, we can't compare. These ones are not consistent. Okay. The next thing it says is power of a test. The power of a test is 59. So this is kind of coming back to the probability. What power is? It's the probability of correctly rejecting the null hypothesis. So in the context of this, it's the probability of saying pH doesn't equal 7 when in fact the pH doesn't equal 7. So if you want to say this, what we would say is that if the true mean mu is equal to 6.8, there is a 0.59 probability that the researchers will find convincing evidence for the alternative hypothesis. So in this case, that mu doesn't equal 7. Basically, it's the probability of correctly rejecting the null hypothesis. So in this case, the more powerful the test, the more likely you are to reject the null in this case. So the ways that you can increase power, there's a few. The easiest way to do it, the easiest way to increase power is to increase n, the sample size. That's the easiest way. If you actually increase your sample size, what happens is it reduces your variability. So what it does is, again, I've used this example before. If this was a sample size of n, if I make it 4 times n, this is kind of what my curve ends up looking like. So that would be 4n of a sample size. What happens is when you do that, you actually reduce that variability. You kind of condense the curve. There is a greater chance of you correctly rejecting the null hypothesis. So that's what we talk about when we talk about power. We could talk about type 1 and type 2 errors here. In this case, we rejected the null. So in this case, since we rejected the null, we have a potential type 1 error. And what in this case is we rejected the null when we should not have. That's what it's saying. We said the pH level differs from 7 when it actually doesn't. And a consequence of this, so if we want to think about a consequence, a good consequence to describe in this one is, we don't use this water source. And then we have, in case we don't use this water source, and maybe we spend money on bottled water instead. So what we're doing is we're wasting money. So that's our type 1, type 2 error. Easy way to remember the difference between type 1 and type 2. This is the way I'll teach you. If you fail to reject, you make a type 2 error. Whereas if you reject, you make a type 1 error. So hopefully that helps. Again, there's a practice I'm going to have you do today and turn in. Just the more you practice on this, the better. What we're going to move on to next is we're going to move on to a 2-sample test for difference in means. And then we're going to do a 1-sample test for mean difference. Please let me know if you have any questions. Hopefully that helped.